Hello everyone, welcome to the 29th session of the course Experimental Methods in Thermal Engineering. In our previous lecture, we have seen the measurement of thermal conductivity as well as the heating value of a fuel. In this particular lecture, we will concentrate our discussion on the measurement of convective heat transfer coefficient and heat flux. Okay. So convective heat transfer coefficient and heat flux are two very important parameters which are actually required while we are doing the experiments involving flow of fluid and heat transfer. Okay. So what we will do over here, first I'll start with the discussion for measurement of convective heat transfer coefficient, particularly in case of forced convection. Okay, so we know that from our fundamental knowledge of the heat transfer that we may have two different situations of convective heat transfer when we are having actually bulk motion of the fluid and that motion is actually having very high Reynolds number of the flow. Corresponding to that, our convection effects will be nothing but forced convection, and if we are having actually temperature driven flow of the fluid, that we normally refer to as natural convection. Okay, however, if we have to quantify that how to find out that whether our natural convection is dominating or forced convection is dominating in a particular phenomenon, what we do, we take nothing but non-dimensional parameter, which is nothing but square of Reynolds number divided by Grashof number. Okay. So if the value of this number is very large than 1, in that case, we say that our Reynolds number is nothing but it characterizes the flow. Okay. So it means in this particular case, our flow of the fluid is mainly governing the heat transfer in comparison to the Grashof number, where Grashof number actually represents the flow which is induced because of the temperature effects, okay, or buoyancy forces. So in this particular situation, we will be having nothing but the dominance of forced convection, and if we are having the value of this particular number very small in comparison to 1, then we may say that our phenomenon is nothing but dominated by natural convective mode of heat transfer, and if this ratio is nearly equal to 1, in that case we will be saying that we are having the situation of mixed convection. Okay, so we cannot neglect any of the effect uh, of either forced or natural. In that particular case, what we have to do, we have to determine the heat transfer coefficient for both the effects, forced convection effect and natural convection effect, and then we have to determine or specify overall or equivalent heat transfer coefficient for the total phenomenon. Okay. So now what I'll be doing, because heat transfer coefficient is a parameter which is like very generic and may be generally is employed for large number of flow or heat transfer configuration. Okay, so we may have flow over a flat plate, flow over a cylinder, flow over a sphere, or flow through a pipeline. So we may have large number of combinations where we are having the involvement of heat transfer and fluid flow. Okay, so for all such type of situations, we may have to determine the value of heat transfer coefficient as well as the heat flux. So what I will be doing in this particular lecture, I'll try to take up few very standard approaches for measurement of heat transfer coefficient, and particularly these approach, whatever I'll be describing over here, this is of generic nature, like this can be employed for any other configuration also, but in particular to describe the overall process of heat transfer coefficient measurement, I'll take over here a specific case. Okay, so in this particular first arrangement where we want to measure the forced convective heat transfer coefficient, I have taken a situation where we are having nothing but a heated pipe and flow of water is happening through this heated pipe. Okay, so what are the primary measurements which we need to do? So then normally we know from our Newton's law of cooling that Q is nothing but, or I should write it, total heat transfer rate Q, that will be nothing but equal to H times area into temperature of the surface minus temperature of the fluid. Okay, so I can write same Tm I am writing as Tbm as bulk mean temperature of the fluid. So that is normally our equation for rate of convective rate of heat transfer. Now if I divide this Q by area, so I'll be finding nothing but heat flux. So heat flux is nothing but equal to H times Ts minus T bulk mean temperature. Okay, so that is like bulk mean. I am referring to the situation that we will be having some temperature of the fluid while it is entering to the pipe, and it will be having some temperature while it is leaving from the pipe. Okay, so if we are applying this particular equation for the entire pipe surface, then obviously we have to take the value of bulk mean temperature. However, we may measure the temperature at specific locations, and based on that also we can actually obtain the value of heat transfer coefficient. Okay, so this is actually the main governing equation. So this main governing equation, if I consider H as my unknown parameter, which I have to actually obtain experimentally. Okay, so what are the primary measurements I have to do? So from here you can see that the very first primary measurement I have to do is nothing but I have to measure the temperature of the pipe surface. Okay, at the same point of time I have to determine the bulk mean temperature of the fluid. So obviously for determining the bulk mean temperature of the fluid, I have to do the measurement of temperature of fluid at different locations along the length of the pipe. Okay, and the very important parameter, third parameter we have to measure is nothing but the amount of heat flux whatever we have supplied. Okay, so that we have to measure. Okay, so now let us try to see our configuration of the experimental setup which I have given over here. So in this experimental setup we are having a pipe. Okay, so in this pipe, because I have to measure the temperature of the water, so therefore I have included a thermometer at the inlet. Okay, so which will be giving the water temperature at the inlet to our test section, and also we are having one more thermocouple at the outlet of the test section which will be giving the corresponding fluid temperature. Then obviously what we have to do, we also, if we want to measure the, because whatever the convection will be happening or the heat transfer will be happening from the tube surface to the fluid medium, so that will be significantly dependent upon the rate at which water is flowing through the pipe. Okay, so for that case what we have to do, because heat transfer coefficient will be nothing but a strong function of the flow rate of the water, so that's why we have employed one flow meter also over here in order to determine the mass flow rate of the water. Okay, so how much how much mass of water is actually flowing. So for that, determining that one, actually we have employed one flow rate flow meter over here. Now what we have done in this particular test section, we are having actually some heated heater arrangement. Okay, so over here we will be nothing but having some heater on the surface of this pipe. So I can also consider this pipe surface as nothing but a conductive, and I can actually connect this surface of pipe to some device which will be actually supplying our electrical energy. Okay, so you can see over here we are having nothing but a over here we are having some transformer, high current transformer, which will be actually converting the giving us the high value of current, so that we may have high heat flux we can obtain, because nothing but we are doing over here joules heating, so that will be proportional to I square R. R will be the resistance of this pipe periphery. If I am taking this pipe as nothing but electrically conductive. Okay, and I will be the amount of current which is passing through it. Okay, so now what we will be doing, like we have to find out this voltage and current whatever we are passing through it. So for that we are having voltmeter and ammeter we are using over here. Okay, now what will be happening if we are having the steady flow situation, then corresponding to steady state heat transfer condition, then corresponding to steady state heat transfer condition, what will be happening, whatever the electrical energy we are supplying. So if I call this Q as nothing but equal to voltage into current, so this is nothing but the amount of electrical power which we are supplying. And now what we have done, this periphery of the pipe surface, actually we have we are having nothing but a insulation. Okay, so we are having insulation over it, so it means this insulation will be preventing the flow of heat transfer in this radial outward direction. Rather, it will actually concentrate the entire heat to flow into the radial inward direction and enter into the fluid which is flowing through the pipe. Okay, so if we consider that corresponding to we are having nothing but steady state heat transfer condition we have achieved, in that case what will be happening, we will not be having any change in temperature of the pipe surface at any particular location with time. Okay, so we may have different temperature at different locations on the surface of the pipe. However, that value of temperature at each and every location will not change with time. Okay, moreover, whatever the inlet and outlet temperature of the water we will be getting, that will also not be a function of time, that will be once again remaining constant with time. Okay, so under such a situation, if we are considering a perfect insulation, we can say that whatever the amount of heat we are supplying, which is nothing but equal to Q equal to V into I, that entire amount of heat is actually being transferred into the water. Okay. Now, what will be happening if I take that my flow is fully developed, hydrodynamically or thermally fully developed. So in that case, what will be happening? We will be nothing but having uniform velocity profile at each and every cross section along the length of the pipe, and that nature of the velocity profile will not be actually changing. Okay, if flow is hydrodynamically fully developed. If flow is thermally fully developed, in that case, what will be happening? Then also the generic nature of the temperature profile will remain same at each and every location. However, the magnitude of the temperature will be actually increasing because we are having heating of the fluid. So obviously the fluid temperature will be increasing as we will be moving along the length of the pipe. Okay. So if we consider such type of situation, and now if we take the assumption that we are having nothing but situation of constant heat flux. Okay, so what we are considering, that we are uniformly heating the surface of this pipe. So because of that, what will be happening? Whatever the heat flux that will be subjected to the fluid medium which is flowing inside the pipe at different locations along the length of the pipe, its value will be remaining actually constant. Okay, so if I consider the situation of a constant heat flux, so simply I can determine the value of heat flux by nothing but Q, which I have measured from this voltage into current, divided by the surface area of this pipe. Okay, so this surface area of the pipe will be nothing but equal to pi times, if di is the internal diameter of the pipe, pi di, and if L is nothing but the length of the test section, so we will be having the surface area as pi di into L. Okay, so from this we can determine the value of heat flux. Now we have employed a number of thermocouples along the length of the pipe. So obviously these thermocouples will be actually helping us in determining the value of temperature of the pipe surface at any particular location. At the same point of time, like if we want to obtain average heat transfer coefficient for the entire surface, in that case what we will be doing, we will be only measuring the temperature of the fluid at the inlet to test section and outlet to the test section, and we will be determining actually bulk mean temperature. Okay, so if we use this particular condition, in that case what will be happening, we will be getting our average heat transfer coefficient. Okay, moreover, over here we are having nothing but the situation of a constant heat flux. Okay, so if we are having a situation of constant heat flux, then obviously at each and every location our heat transfer coefficient has to remain constant, and because our this temperature will be actually linearly increasing along the length of the pipe, both the temperature of the fluid medium as well as the temperature of the pipe surface. Okay, so this particular information actually I am taking from the knowledge of our fundamental heat transfer course, because we know that if we are having the situation of constant heat flux, then what happens in case of a fully developed flow situation, our temperature of the pipe surface as well as the temperature of the fluid medium increases in a linear fashion along the length of the pipe if we plot on temperature versus length curve, and we will be having this temperature difference as constant at each and every location. Okay, so now if we are having the situation of other situation, that if we are having nothing but this surface temperature, say we are maintaining at some constant value, and then we are allowing the fluid to flow through it, then obviously in that case what we have to do, we have to actually measure the temperature of the fluid at different axial locations along the length of the pipe, and corresponding to that we can determine the value of local heat transfer coefficient. Okay, so in this particular situation, what we are basically doing, we are using the fundamental law of convective heat transfer, and our physical situation is such that we are having the primary mode of heat transfer as convective heat transfer only in this particular situation. Okay, and we are not having any other heat transfer over here, and so that's why we have used our primary governing equation as nothing but Newton's law of cooling. Now whatever the parameters we are having in Newton's law of cooling, apart from this convective heat transfer coefficient which we want to determine experimentally, all these parameters actually we have experimentally measured with the help of some instruments. Okay, and then we are employing these parameters into our governing heat transfer equation to obtain the corresponding value of heat transfer coefficient. Okay, so like this we can design indigenous setups for determining the heat transfer coefficient value for different physical situation. Okay, so this is a very generalized idea about measurement of heat transfer coefficient. Okay, now what I will be doing, I will not give a very detailed information over here that how to select what type of instrument is to be employed for measurement of the temperature. So that part particularly I will cover in our last lecture. Our last lecture I'll be taking on Monday, and in that lecture particularly I'll be discussing about the design of experiments. Okay, so like if you have to design the experiment from the starting itself, that how to fabricate your setup, what type of instrument you have to use, what type of measurements you need to do. So there I'll take this particular example, and then I'll discuss this particular example in very detailed manner in order to take different types of measurements and what type of instruments we have to employ. Okay, so in this particular discussion I have just given you the general idea of measurement of convective heat transfer coefficient, particularly for a situation where we are having forced convection and flow of the fluid is actually happening inside a circular pipe. Okay, heated circular pipe. Now another situation I have considered over here, that is nothing but of free convection heat transfer coefficient. So here we are considering that we are having a rod, and this particular rod is of actually diameter d, and inside this rod actually we are having some heaters mounted. Okay, so obviously when we will be supplying electrical energy, we will be having nothing but generation of heat. So in order to maintain the surface of our test section at a constant temperature condition, we have to avoid edge effects. So that's why what we have done, we have considered two guard sections where we will be having the guard heaters, which will try to maintain the temperature of this test section almost at uniform condition. Okay, so this is our test section which is having length L, and now what we are having basically, we are nothing but this heated rod is actually present in our ambient. So obviously when air will come in contact with this heated rod, the temperature of the air will be increasing and its density will be decreasing. So because of that, air will try to move in upward direction due to the buoyancy forces, and we will be having actually replenishment of the that particular volume which is evacuated by the rise of the air with subsequent cold air. Okay, so in this particular type of arrangement, we will be having nothing but the establishment of some natural convection induced flow of fluid, and we will be having continuously the transfer of heat from this hot surface to the surrounding air. Okay, so what we are considering over here, that the temperature of the surrounding air is nothing but T infinity. So now if I say that whatever the heat flux we are subjecting in this particular test section, so obviously that we are measuring with the help of the electrical input, so that heat flux will be nothing but equal to HA times TW minus T infinity, where we are considering that the surface of this heater is maintained at temperature TW. Okay, now in this we are not having any insulation over here, so obviously what will be happening, we will be having some loss of radiation heat transfer also. So sigma times epsilon into A, if A is nothing but surface area of this particular test section and epsilon is emissivity, TW4 minus Ts to power 4. Okay, so that will be like our governing equation. Now in this governing equation, area already we are knowing, and the temperature of this particular wall we can measure with the help of thermocouple. T infinity also we are measuring, and Ts also I am taking the temperature of surroundings. Okay, so surrounding temperature also we are knowing. So probably if this uh, heater is placed in a large enclosure, then obviously the temperature of surroundings will be identical to that of the temperature of the air. And if it is placed in a small enclosure, then obviously we have to consider this Ts as nothing but the temperature of this surface of the enclosure. Okay, and area we are knowing from geometric consideration, sigma is constant. So if in our situation we are having actually the consideration of radiative heat transfer also, then we should know the emissivity of this surface. Okay. However, what we do, because many of the times then measurement of emissivity is also a difficult task. So what we do, we try to coat this particular surface where we want to measure the convective heat transfer coefficient. We try to coat this particular surface with chrome or nickel. So basically what will be happening if we are coating this with chrome, very thin layer of chrome. So in that case, we will be having actually the dominance of convective heat transfer, and the radiative heat transfer will be negligible in comparison to convective heat transfer, and then we can remove or we can neglect this particular radiative heat transfer term from our governing equation. Okay, so this is how like we can determine the value of, and obviously this heat flux we are already knowing from our voltage into current measurement. So we will be able to determine the value of heat transfer coefficient. Okay. So from this particular discussion, you might have observed that we are not having any standard measurement device or instrument for determining the value of convective heat transfer coefficient. Rather, depending upon the physical situation where we have to do the measurements. Actually, we are nothing but employing the our general heat transfer laws, and with the help of these laws, then we are developing some indigenous measurement arrangements for obtaining the corresponding value of convective heat transfer coefficient. Okay, so convective heat transfer coefficient is like a very wide topic. You might have seen if you have taken a course on convective heat transfer. There we are having actually a large number of physical situations, and if we simplify some of the situations, then we can theoretically determine the corresponding value of the convective heat transfer coefficient. And we are having a large number of empirical correlations are also available, which are actually derived based on the experimental measurements for different type of physical situations. Okay. So this is a like very broad topic, and it's even a area of research for different type of complex situations where we are having the difficulty in measuring accurate value of convective heat transfer coefficient. Okay. Now another type of measurement what we do in our fluid thermal systems, that is nothing but the measurement of heat flux. Okay, because what we have to do for many situations, we consider that if we are knowing the value of heat flux, then by just knowing that heat flux value, actually we are employing it for further calculation of other type of measurement. Okay, so one of the heat flux meter that is used, that particular meter is known as slug type heat flux meter. So what we are having in this slug type heat flux meter, basically this is the heat flux which is coming from some source. So what we do, we place our source, and this particular source will be of nothing but, initially when we will be starting the measurement, then we are not knowing the exact value of heat flux, that how much heat this source is actually emitting. Okay, so initially we will be considering this nothing but a source of unknown heat flux. Okay, we are not knowing the exact value of the heat flux. So initially we are having some unknown heat flux which is coming from this particular source. So what we will be doing, we will be placing some conductive device over here. So that particular conductive device we are called conductive material we are calling as slug, and across this slug we will be having actually a layer of insulation. Okay, and then at the surface of the slug, and as well as at the interface in between the slug and the insulation, we will be placing some thermocouple. Okay, so these thermocouples will be actually giving us the value of the temperature. Generally we try to take the characteristics of this slug material as nothing but high thermal conductivity and small size. Okay, so if we are having high thermal conductivity and small size, in that case, what will be happening? Our temperature of this slug surface will be almost constant. Okay, so now means temperature of the slug surface will be actually uniform at each and every location. It will not be constant, it will be changing obviously with time, but what will be happening actually with the spatial location, it will remain constant. Okay, so now if we are subjecting this particular slug to the unknown heating source, so we will be getting some heat from this source, and obviously what will be happening, the temperature of this slug will be actually changing with time. Okay, so what we are doing, we are considering that this Q is nothing but a unknown heat flux which is actually subjected over here, or unknown heat transfer rate. Okay, so if Q is unknown heat transfer rate, and if A is nothing but the area of this particular slug surface, so Q by A will be equal to M into C dt s by d tau. So tau is nothing but taken as over here as time, and dts we are saying that change in temperature of this particular slug in time delta tau. Okay, so this equation we are writing on per unit area basis. So that will be nothing but equal to U times. So after what we are considering that we are having a thermocouple which is giving nothing but the temperature of this particular slug, and we are having one more thermocouple which will be giving us nothing but the temperature of this insulating wall. Okay, so for TW is nothing but our temperature of wall. So whatever the insulation wall we are having, its temperature is equal to TW. Okay, so U we are considering that nothing but coefficient, or I should say yes, I can write it as nothing but coefficient of heat transfer only. So we will be having actually the transfer of heat at this particular junction from the slug to this insulating wall. Okay, so for that, whatever the coefficient of heat transfer we are having, that is nothing but equal to U. Okay, so now what we can do, if we know the value of U, temperature, we can measure with the help of thermocouple. So we are knowing this measurement of this particular temperature also as function of time. So by knowing these particular values, actually M and C for this slug material will be already known, so we can determine the value of this unknown heat flux which is subjected over here. Okay, now one important consideration we have to take, that our size of the slug should be small and its conductivity should be high. Otherwise, what will be happening, we will be having actually variation of temperature across the surface of the slug. Because of that, actually we have to go for even complex heat transfer analysis for determining the for including the effect of spatial variation of temperature within our slug also. Okay, so this type of flux meter is particularly known as slug type heat flux meter. Then another type of meter for measurement of heat flux is something which is known as garden foil type heat flux meter. So what we are having in this also, we will be having actually unknown source over here. So this unknown source, from this unknown source we will be getting heat, and that heat will be subjected to a very thin disk. So we are having over here this very thin disk over here. So this thin disk is nothing but made up of constantan, and below that we are having nothing but a copper heat sink. So here we are having another material. That particular material is nothing but copper, and it will be acting as heat sink. So that will be maintained at some low temperature. Okay, so now what we will be doing, we will be placing one wire over here at particularly at the center point of this uh, disk, and moreover that also will take at the contact in between the copper and the constantan surface. Okay, and another junction we will be taking particularly of the copper only, and what we will do, we will try to measure actually the EMF produced across these two copper wires. Okay, so in this configuration, nothing but we are this configuration is particularly becoming identical to that of a thermocouple configuration. So in this thermocouple configuration, we are having one junction at this particular point and another junction at this particular point. So what we will be finding, we will be nothing but finding the temperature difference in between these two radial points. Okay, so we will get the value of this EMF, that will be nothing but proportional to so whatever this output EMF I will be getting, that will be proportional to delta T, where delta T is nothing but the temperature difference in between the center, okay, and the other radial, any other radial location which we are having actually over this disk surface. Okay, so in this type of particular device, what will be happening, whatever the heat we are supplying, because this particular heat copper heat surface will be maintained at some constant temperature, so whatever the heat we are supplying to this constant disk, that heat will be actually traversing in the radial direction over the surface. Okay, so we will be having some gradient of temperature in the radial direction. So depending upon the measurement of temperature in the radial direction, we will actually try to determine the value of heat flux. Okay, and another type of heat flux meter, which particularly operates on the principle of conduction heat transfer. In this arrangement, what we do, we once again try to make some thermocouple-like arrangement only. So here you are having nothing but a thermoelectric material B. So this gray shade over here, nothing but so B type thermoelectric material, and this plain color over a white color over here shows nothing but a thermoelectric material A. So what we have done, we have joined these two materials. So this is one of the junction, this is another junction, this is another junction, and in between we have placed some other material. Okay, so this is like one more junction, this is one more junction. Similarly, what we will be having, we will be having nothing but the corresponding junctions on the lower end of this particular arrangement. Okay, so in the lower portion also we will be having some junctions. So what we will be now doing, these junctions now will be subjecting to the high temperature. Okay, so obviously what will be happening now, these top junctions will be becoming nothing but at high temperature, because these are exposed to the unknown heat source, and bottom junction whatever we are having, in this particular bottom junction we will be having some low temperature T2. So I am considering that temperature of the top junction is T1 and temperature of the bottom junction is actually T2, and S is our thickness. So now what basically is happening, we will be having some conduction of the heat from top junction to the bottom junction, that will be actually controlling this temperature of T1 and T2. So now we are having some thermoelectric material. So if we try to once again measure the EMF, and if we maintain the one of the junction at some fixed temperature, particularly the lower junction. So what we can do, obviously for this thermoelectric materials at the junction, we will be knowing the thermal conductivity of the material. So whatever the heat we are getting from this unknown source, that will be actually conducting from top to the bottom direction. So what we can do, by applying the Fourier's law of heat conduction, we can determine the corresponding value of the heat flux over here. Okay, and for the measurement of temperature, actually we will be nothing but getting some EMF which will be generating because of the thermoelectric effect which we are having over here. Okay, so this particular arrangement is nothing but becoming identical to that of a thermopile like thermocouple, where we are having actually number of junction points. So over here our EMF will be actually amplified. Okay, now with this particular discussion, like our general idea for measurement of measurement of convective heat transfer coefficient and heat flux is like over. But apart from that, I will also try to briefly discuss some of the techniques for detection of the radiative heat flux. Okay, because if you recall to our previous lecture, there we have seen one of the measurement of temperature uh, based on the radiative heat transfer. So there we have considered that already we are knowing the value of radiative heat flux. Okay, so obviously we should know that what are the different devices available for measurement of the heat flux because of the thermal radiation. Okay, so this particular topic is not in the given in your syllabus, so this is something which is beyond your syllabus. So that's why I'll not go into much details of the different devices. But what I'll be doing, I'll be briefly describing the different devices which are available for measurement of thermal radiation, just for the sake of completeness. Okay. So, general idea for measurement of the radiative heat flux is nothing but that if we are taking some source from which radiations are emitting, we will be subjecting these radiations to focus on some small element. Okay, so we may have small circular disc, or we may have some plate type small device over which we will be actually, this particular device will be exposing to the radiations which are coming from a source. Okay, now obviously if we place this particular device into some medium, so for example if this plate, we are having some plate, and here we are having the source, so from the source some radiations are coming. Okay, so we are having radiative flux which is subjecting to this particular plate, and now this plate is placed in air. Okay, so what will be happening if this is placed in air, then obviously from the surface of the plate there will be some transfer of heat because of the convection into the surrounding air. Okay, so we will be having some convective heat transfer. At the same point of time, obviously, when we are placing this plate, so we will be having some fixer which will be actually holding the plate. Okay. So what will be happening then at this particular junction from plate surface to the fixer, we will be having some conduction heat transfer, and heat will be actually transferring from the surface of the plate to this particular fixer. So we will be having some loss because of the conduction heat transfer also. Okay. So if we are considering this generalized situation, then obviously measurement of radiative heat flux will be difficult, because if we have to accurately determine the value of radiative heat flux, then obviously we have to measure the corresponding loss because of the conduction and convection. Okay, because ultimately what we will be doing, we will be just with the help of a thermometer, we will be determining that how much rise in temperature of this plate is happening. Okay, and that rise in, if we are considering that we are having negligible conduction and convection effect, in that case what will be happening, whatever the radiative flux we have subjected to Q radiation, that will be nothing but equal to epsilon of that particular source from where we are getting these radiations times sigma T to power 4. Okay, so this is nothing but Ts power 4 minus this plate whatever I have taken Tp power 4. Okay, so like this plate I am considering over here. So this is how we have to determine actually, by just knowing the value of the plate temperature and the surface temperature from where the radiation is coming, we can determine the value of radiative heat flux. Okay, so what we have to do basically at this particular source also, we have to employ some thermocouple, and at the same point of time at this plate surface also we have to employ some thermocouple. Okay, so this is how like we can determine the value of radiative heat transfer. So in general what we do, we are having few standard commercial devices available for determining the value of radiative flux. So such devices are known as actually radiometer. So before that, what we have to do, as I have told you, that we are having, if we are having this plate taken in some air medium, so we will be having loss because of the convection, and moreover at the fixer also we will be having some losses because of the conduction. Okay, so to avoid this, what we do generally, we try to place this particular plate inside some enclosure. Okay, and what we do, this enclosure actually we try to keep in absolute vacuum situation. Okay, so if we are having absolute vacuum over here, then obviously we will not be having any convective heat transfer because it requires medium for the transport of the heat. At the same point of time, if we take some insulated supports over here, perfectly insulated supports over here to fix this or to hold this plate, so in that case also what will be happening, we will be having almost negligible conduction losses. So what will be happening, whatever the radiations we are actually exposing, this will be mainly employed in rising the temperature of this particular surface. And moreover, one more thing we have to consider over here, that size of this plate should be very, very small, so that the thermal, we are not having much thermal inertia of the system, and our device is actually having good transient response. Okay, so in order to do so, what we have to do, whatever the enclosure we are considering, in this particular enclosure we should have some optical access. Okay, so our material of this enclosure at a particular section, at any particular location, should be actually such that it is allowing the optical access. Okay, so generally what we are having in case of thermal radiations, the spectrum of wavelength is 0.1 to 100 micrometers. Okay, And in this we are having some visible light also, small portion of the ultraviolet also, but majority of the portion is nothing but our infrared radiations, okay, IR radiation. So that's why what I have done in this next slide, I have included one table, and this particular table nothing but tells the infrared transmission characteristics of several optical materials. Okay, so you can see that the wavelength we are considering from zero point 0.8 to 100 micrometer in our infrared region, and then depending upon the wavelength which is coming from our source, we can actually choose that what type of material we have to use to fabricate our enclosure, which will be actually holding our main sensing device for determining the value of corresponding radiative reflex. Okay, so these are the different materials given over here, and then corresponding spectrum of wavelength within which they will be allowing the optical axis. Okay, now this is a device which is used for measurement of the uh, radiative heat flux. So that particular device is known as radiometer, and this particular radiometer is actually utilizing a thermopile sensor. Okay, so this is nothing but a photograph of a commercial thermopile. So you can see over here we are having this optical window through which actually we will be subjecting the radiations, thermal radiations to focus at this particular junction. And at this particular junction, we are having the thermopile sensor arrangement, which will be actually determining the temperature. Okay, so how this particular central location I have given over here, you can see this is a schematic representation. So in this, we are having this black colored central core, and outside that we are having this small strips over here also. So this is nothing but these small strips outside represents the cold junction. Okay, because what we are doing, whatever the heat which is coming because of these radiations, that is nothing but focused on this central portion. Okay, so all the radiations are actually focused on this particular zone. So in this central zone, we will be nothing but getting the hot junction, and whatever outside we are having this particular material, that will be nothing but acting as a cold junction. So now we are having some connections over here. So with the help of this, we will try to measure the value of EMF. So that EMF will be nothing but if we are maintaining this cold junction at fixed temperature, so the value of EMF will be nothing but a function of the temperature of the hot junction, and particularly the temperature of the hot function will be nothing but controlled by only because of the radiations. Okay, so radiative flux which is subjected to this particular junction. So by just knowing the temperature, we will be actually able to calculate the amount of radiative heat flux. Okay, so that is nothing but that will be coming from our generic equation of Stefan Boltzmann law. Okay, so this is the like whole idea of using a radiometer, and this particular I have given you the photograph of a commercially available radiometer. Then this is one more device which is actually based on thermistor. So in this previous device, nothing but we are having thermopile arrangement. So by meaning of thermopile arrangement, we are saying that we are having nothing but thermocouples for measurement of the temperature at this particular source. Okay. Now, in case of this second device, what we are having actually thermistors for measurement of the temperature. So the idea of using the thermistor is actually it is having more transient response, sorry, fast transient response in comparison to that of a thermocouple. So that's why many times we go for thermistor based radiation detectors also. Okay, then one more, so this is the like detailed layout of a radiometer which is based on the thermistor detector. So nothing but you can see over here that this is our main source from where we are getting the thermal radiations. Then these thermal radiations are passed through a number of mirrors, and the location of the mirrors is arranged in such a fashion so that our entire light is actually focused on a single junction. Okay, so this is the main junction over here where we are actually focusing our entire light, and at this particular junction what we will be having, we will be having uh, some arrangement, something like this, where we will be having actually thermistor sensing element. Okay, so this particular thermistor sensing element, depending upon its temperature, it will be giving us the corresponding change in its resistance. Okay, so for measuring that change in resistance, what we have to do, we require some electrical circuit. So this is the block diagram of that electrical circuit is given over here, which is required for measurement of the temperature. Okay, and moreover, what generally happens from the thermistor, we will be getting actually our value of the output signal in a very small range, as magnitude will be very small. So that's why we require some amplifier also. So you can see over here that we are having some electronic circuit which involves these different devices for obtaining the final output. Okay. Now, generally what we have to do when we are using the radiometer, so what we are saying that we are actually basically doing the measurement of, we are doing the measurement of radiation flux based on the measurement of the temperature. Okay, but many of the times what we do, we need to require some device for calibration of the radiometer. Okay, so for calibration purpose, what we do, we have to actually construct some black body. So for the black body, what we do, we are having this conical cavity material over here, and we are measuring actually, we are having some resistance thermocouple mounted over here, and across this particular body, we are having actually some heater coils. So obviously, what will be happening with the help of this heater coils, we will be actually heating the temperature, heating this particular body over here, and whatever this body we are having, this is nothing but of high thermal conductivity. So if it is having high thermal conductivity, so at each and every location of this body, we will be having actually the same temperature value. Okay, and this conical surface, whatever we are having internal surface, generally this conical surface is actually blackened with the help of some coating of the material. Okay, so now what will be happening, if we have to calibrate the device, obviously then we should have some source of known radiative flux. Okay, and then obviously what we will be doing with the help of the known radiative heat flux, we will try to measure the output EMF, and then we will try to relate it to the temperature. So if we say that we are having a black body, in that case what will be happening, black body radiation will be nothing but equal to sigma times Ts to the power 4, where Ts will be the temperature of this surface, which will be obtained with the help of this RTD. Okay, and we are considering that the radiation emitting characteristics of this surface is nothing but identical to that of a black body. So particularly if we take this conical type cavity, then the characteristics of the this particular surface as a black body is nothing but within the uncertainty limit of 1%. Okay, so what we will be doing over here, we will be placing our radiometer, which we want to calibrate. So radiometer will be placing over here. So obviously whatever the radiations now will be emitted from this body, that will be passing through this front aperture, and it will be actually focusing on the radiometer junction. Okay, so we are having this number of baffles given over here. So the idea of giving the baffles is that it should not focus any radiations from the surroundings. So whatever the radiations from the surroundings will be coming, actually these will be obstructed by the baffles. So only the radiations which are coming from this particular source, these will be actually falling on the radiometer. Okay, and now as we are saying that we have nothing but made this surface identical to that of the black body, so we can say that whatever the radiative heat flux we are subjecting over here, that is nothing but equal to sigma times Ts to power 4. Okay, and one more thing, like if we have to vary the amount of radiative heat flux, whatever we are subjecting in this particular front aperture, so that we can vary by varying the temperature of this conical material over here by just changing the current which is flowing through this heater coil. Okay, so this is the characteristics of some thermal receivers. So generally we are having response time of a thermocouple in of the order of 0.2 second, whereas thermistor is having 3 millisecond and metal bolometer is having 4 millisecond. Okay, and this is the corresponding energy threshold. So by meaning of energy threshold is nothing but this much amount of radiative heat flux is required to change the output of this particular thermocouple device by unit value. Okay, then we have this measurement of emissivity also. So many of the times what happens, so in our previous discussion we are considering that emissivity of the surface for which we want to measure the temperature that is actually known. Okay, but in actual practice that may not happen. So we require certain instrument for measurement of the emissivity also. So for measurement of the emissivity, we may use thermopile radiometer. So in case of thermopile radiometer, what will be happening? Once again, we will be having a heat source, and whatever the sample for which we want to measure the emissivity, that sample we will be placing close to our heat source. So over here you can see this is nothing but our sample, and here we are having heater, and then here we are having some copper plate which is actually providing the heat from the heater to this sample. Okay, so now this sample will be giving the radiations, thermal radiations it will be emitting depending upon its temperature. So we are measuring the temperature with the help of thermocouple, and whatever the radiations, thermal radiations which are emitted by the sample, these are nothing but focused on one uh, thermopile radiometer. So here we are having this thermopile. So you can see the detailed view of thermopile over here. And in this thermopile now, this particular point where all our thermal radiations are focusing, that will be acting as a hot junction. And this another point where actually what we have done, we have provided some rear shield which will be avoiding the radiations to fall on this particular surface. So this will be nothing but acting as cold junction. Okay. So now as this arrangement is acting as a thermopile, so obviously with the help of the EMF, we will be actually determining the temperature of this hot junction. Okay. So once we are knowing the temperature of this sample as well as the temperature of this hot junction, so what we can do, we can determine the value of emissivity. So by just because over here we are having different optics involved in this particular arrangement. So some of the standard dimensions are also given over here, that this particular L length and this R1 as the radius. So depending upon these values, we will be actually determining the view factor from our sample to the thermopile. So that view factor is nothing but equal to R1 square by R1 square plus L square. Now if we employ over here the radiative heat transfer which is happening from the sample to the thermistor by just because we are knowing now the temperature of the surface as well as the temperature of the receiver. Okay, so these two we are knowing, and FTS is view factor which we have obtained from the geometric uh, calculations, and sigma is constant, and epsilon s is nothing but the emissivity of the material. So emissivity of the material will be 7.84 times E divided by this particular denominator. Okay, so where E is nothing but the amount of radiations which are emitted. Okay, so now what we have done over here, we are actually providing some heater input. So for this heater, whatever the power we will be supplying, we will be actually measuring its voltage into current. Okay, so E will be nothing but V into I divided by area of this sample. So the area of the sample from where actually we are getting nothing but the thermal radiations. Okay, so by using this particular standard setup, actually we can determine the corresponding value of the emissivity of a surface. So from this particular discussion, you can see that the overall governing equation, whatever we are using, that is nothing but a Stephens-Boltzmann equation. In few cases, we are actually already considering that we are knowing the emissivity of the source. So if we are knowing the emissivity of the source, then actually we are using that equation for determining the value of radiative flux by knowing the values of the temperature. And in case if we are not knowing the emissivity, then we are making some indigenous arrangement with the help of which we can determine the value of the radiative flux. And once we are knowing the radiative flux, then by just knowing the value of temperature, we are actually back calculating the value of the emissivity. Okay. So another like after this, we may have because in this particular slide I have discussed the measurement of emissivity. Apart from emissivity, we are having actually important properties of absorptivity. Then we are having transmittivity, reflectivity of the materials. So these other different properties also we are having some standard devices available for measurement, but as these are not the part of the syllabus, even emissivity is also not the part of our syllabus, but just I am showing briefly over here for your knowledge. Okay. Then because many of the time we go for measurement of solar radiations, if you have to do any solar installation. So we should know that what amount of solar radiations we are receiving in that particular location, and depending upon that only we can actually design some devices for conversion of solar energy either into electrical energy or thermal energy for obtaining some desired output. Okay, so generally what happens, whatever the solar radiations we receive from the sun, these are not, overall trend is not identical to that of black body radiations. However, whatever the broad spectrum we see, that is nothing but follows the behavior to that of black body radiations. Okay, so you can see these are the solar radiations, spectrum of solar radiations which are coming from the sun. So you can see the wavelength is changing from zero point 0.2 to 2.2. So zero point 0.2 to 2.2 micrometer. This is a very narrow spectrum of wavelength through which we are receiving actually the radiations from the sun. And normally all these radiations are actually of very high energy radiation. Okay, so I have plotted over here three different curves which shows the variation of the radiative flux as function of the wavelength. So the very first curve is taken at outside the atmosphere, another is taken at sea level when incident angle of the radiation is actually 0 degree from normal, and third curve is actually shown when we are having once again we are measuring the radiations at sea level, but incident angle is having value of 78 degree from the normal. Okay, now in these all these three curves, one similarity we are having, that we are having the peak value of the radiative flux is nothing but corresponding to that of almost uh, zero point 0.5 micrometer wavelength. Okay, so now if we consider that our lambda max is nothing but equal to zero point 0.5 micrometers, and if we consider that we are having the situation of thermal equilibrium in between our sun and the atmosphere. So in that case, what will be happening? By just applying the Wien's displacement law, we can determine the value of temperature at the surface of the sun. Okay, so if you use this equation, you will be finding the value of temperature at the surface of the sun close to 5795 Kelvin. Okay, so this is something when we are considering that our spectrum of the radiation coming from the sun is nothing but following the spectrum of black body. Okay, and another assumption we are taking that we are having the peak wavelength corresponding to that of zero point 0.5 micrometer. Okay, so the rough estimate for temperature at the surface of the sun comes from here is nothing but equal to 5795 Kelvin. Okay, so now what we want to do basically at different situations where we want to do the solar installation, we want to measure the amount of radiative heat flux available. Okay, so there are two different measurement devices which are used for determining the value of solar heat flux. So one of the devices is actually pyranometer, which is very commonly used device and commercially available. Okay, another type of device is particularly known as pyrheliometer. So pyrheliometer is actually based on the principle of collimated radiations, where all the radiations, whatever we are getting from the sun, we will try to focus at some particular incident angle, and we will try to concentrate this with the help of a single incident ray, and then we will try to determine the intensity of that particular beam. Okay, but this device is not that much popular. The more commonly used device for determining the solar radiative flux at different locations, whatever we employ, is nothing but pyranometer. Okay, so this I have shown over here, one of the pyranometer, a clay pyranometer I have given over here. So what we are having in this pyranometer, we are having actually two junctions. So you can see one junction we are having over here. So this particular junction is nothing but subjected to the solar radiation. So this will be acting as our odd junction. Okay, and then another junction we are having at the bottom end, and this particular junction is nothing but a reference thermopile junction. So here we will be having nothing but some heat sink which will be maintaining this reference junction at constant temperature. Okay, so now what we are doing, whatever this odd junction we are having, this actually we have enclosed inside some glass enclosure, and what we are doing, we are actually maintaining complete vacuum over here, so that we are not having any losses of heat because of the convective heat transfer. Okay, And whatever the glass we are having, which is exposed to the sun radiations or solar radiations, that is of actually hemispherical shape. Okay, so we are nothing but considering the total hemispherical spectrum of the radiations which are coming from the sun, and these radiations we are incidenting on a single point. So what will be happening, because we are having one reference junction, we will be having one hot junction. So at any particular location we will be actually fixing this our pyranometer, and we will be determining the value of the temperature of this hot junction. Okay, so whatever the amount of radiations this hot junction has received, that will be nothing but proportional to sigma t power 4. By knowing that only we can determine our value of E, whatever the solar radiative flux we are receiving. Okay, so this is basically based on the principle of two concentric rings. So we are having two concentric rings. One of the ring will be serving as hot junction, and another will be serving as cold junction. And generally we employ 50 element thermopile arrangement. Okay, in order to determine the value of temperature. Then the rings which are at hot junctions, these are actually coated as black, and the ring which acts as cold junction, this is coated with white to produce a temperature difference. Okay, when it is nothing but exposed to the solar radiation. Because if we are having the difference of color in between the two rings, so what will be happening, all the solar radiations which will be incident on the black color, this will be actually completely absorbed, and all the radiations which will be incident on this white color, this will be completely reflected. Okay, so one we will be finding as a hot junction, and another we will be finding as a cold junction. Okay. Generally, what we do the coating of barium sulfate in order to make this particular white junction. Okay, and we cover these two rings, whatever we are using in our device, with glass. So generally, whatever the glass we use, hemispherical glass, that allows the thermal radiations within the spectrum of 280 to 2800 nanometer. Okay, and a typical sensitivity of this type of device is nothing but equal to 107.5 millivolt centimeter square per watt. Then another type of pyranometer also we are having, which operates on the principle of differential expansion of the bimetallic strip. So already I have told you the principle of bimetallic strip while we were using actually the measurement of temperature. So what will be happening when the bimetallic strip will be exposed to the solar radiation, then depending upon the temperature of the junction, we will be having nothing but bending of this bimetallic strip. And what we can do, we can employ some mechanical linkage and some mechanical readout arrangement, which will be actually depending upon the change in curvature of this bimetallic strip, will be giving us the indication of the temperature. Okay, so this is also one device which is many times employed for continuous estimation of the solar radiations throughout the day, because it doesn't require any external power source. Okay, apart from that, by just using the electronic devices, we may go for some indigenous device development using the photodetectors, where photodetectors will be PN type diodes or PIN type diodes on which light will be incident. So they will be nothing but giving some current output. So depending upon that also, we can relate the amount of solar radiations which are incident on the sensing element of the photodetector. Okay. So with this, I'll conclude our discussion on measurement of convective heat transfer coefficient, heat flux, as well as the solar radiative flux. Okay. Particularly the portion which I have covered over here on measurement of radiative flux and solar flux, that is not part of your syllabus. So this just I have included for briefly discussed for your knowledge or complete understanding. Okay. Now what I will do in our next lecture, I will briefly discuss about the data acquisition system, and then after that, in our last lecture, we will have a detailed discussion with the help of a case study on design of experiments. That if we have to devise or identify that what type of instrument we should use, what type of parameters we should measure if we are having a physical situation given for which we have to perform the experiments. Okay, so we'll take up a case study, and with the help of that case study, we will try to see that how to design the experiments completely starting from the scratch. Okay,